Okay, looks like it's good. Go check out YouTube. We are live. 2 viewers, 5 likes. Great. Okay. It seems like we're healthy on all the streaming services. Feel free to drop a chat, say hi, make sure the audio and the visuals are good, all the settings are quality. Feel free to say hi while you're here. Any questions about the FPGA, this development board, or the RP2040. Hopefully I keep track of everything. This is more of a casual stream. We're mostly just going to be talking. This is kind of just my personal projects that I've been playing around with. Nothing that's sponsored or anything. This was a gifted board, but we're just going to be playing around with a few different side projects that I'm interested in looking at. Mostly learning about how the 240 works, the RP240, and how we can use this with an FPGA effectively. I've been really enjoying this. This is a small Spartan 7 FPGA. You don't have much fabric space, so you have to constrain down your design quite a bit. So even the final design today that we're going to look at, there's not enough space to do an internal logic analyzer, an ILA core, effectively without pruning it down a lot. I need to figure out what else I can prune so that we could potentially be more effective with this FPGA. Feel free to say hi in the chat. I'll start. And we'll wait 2 minutes for people to show up. But thanks for joining. I am FPGA Zealot, and this will be a fun little side project today. So interesting, multi-streaming. Okay, not sure how well it's easy to watch the analytics. I don't want to do that today. View event, can I jump to analytics from here? Details, I don't think so. Guess that's somewhat analytics. Okay. Give it another minute, but we'll go ahead and start with the group we have. Okay. So welcome to the stream. We'll be looking at the Raspberry Pi 240 little I/O microcontroller and a Spartan 7 FPGA. This is going to be on the Adivio development board that Adam Taylor was able to get me. I wanted to look at using the PIOs, the programmable IOs on the 240 to transmit data back and forth to the RISC-V, the MicroBlaze V. But I think this would be a fun little project to look at those two kind of unique feature sets on both these devices. I am FPGA Zealot, Andrew Wilson. Let's see, we can go through the next little things here. For socials, this is on YouTube. I'm streaming on YouTube, LinkedIn, and Twitch. I post on X as well. You can find me as FPGA Zealot or Andrew Wilson on LinkedIn. Some disclaimers. This is not a sponsored live stream. This is just me goofing around. I am not employed by AMD. I do not offer official support for AMD or our DVO projects or products. The content of this channel is for informational purposes only. You know, fun little hobby at the moment. And all opinions expressed in this channel are my own. So today we're going to be looking at this board. We're going to be looking at the Raspberry 240 on the left and talking to the Spartan 7 in the middle. And I wanted to see what's the best high-speed communication between these two FPGAs. Or not two, these two devices. One FPGA, one microcontroller. And learning more about the RP2040, they have programmable I/O, where you can have like these really there's these small state machines where you can give a few instructions to assembly and have it go through it real quickly to be able to interact with I/O at pretty fast speeds, which is really cool. And so today we'll be looking at, again, same as last time we looked at this board, we have these 10 lines between the processor and the FPGA. We're going to be doing 5 for RX and 5 for TX. So I first wanted to start with doing a loopback in the FPGA. So let's talk about the FPGA design real quick, and then dig into the RP2040 data sheet. So looking at the FPGA design, this is our first FPGA design. We're gonna be looking at 2 different ones today. We are just taking 5 of the lines here, and we're just connecting them to the output. These are not being clocked. So these are asynchronous signals going from an input on the FPGA to the output of the FPGA. So we're doing no timing, we're doing no registers, we're just basically doing an internal logic analyzer on kind of a wire loopback through the FPGA. And I guess we should look at the sample rate real quick. I think this is a sample rate I was playing around with a video core, so it's kind of fast. 150. So we're doing 150 megahertz sample rate, so we should be able to look at how big these signals are. But the pulses probably won't line up well because we're sampling at a very different clock rate than what's driving the system. But we should be able to see everything pretty well with 150 megahertz oversampling. So that's the design, and it's programmed into the FPGA. And we are going to start here. This is, the default signals, but we're going to use the PIOs. So let's bring out the data sheet so we can talk about these. So here's the RP2040. We're going to use PIO 0 for transmit and PIO 1 for receive. I played around with the code and I got something I really like, but if you guys have any suggestions for improved code, feel free to comment, chat, whatever. We can talk about these different systems. But if we zoom in on the PIOs, we are basically going to do a very basic state machine that's going to use one of the signals as a strobe. So we're going to kind of do a asynchronous strobe data protocol. It's the strobe you could kind of consider like a clock, but it's more going to be a valid strobe that's going to go up and down. And then on the FPGA side and the processor side, we're going to use the rising edge of that strobe to say that the data is valid. There's really not a good way to do, I think, an asynchronous clock system here, especially when there's valid data and not valid data. Both systems, I think, can react well enough for kind of an asynchronous strobe system, so that's what we're going to try. And we're basically going to have a state machine that's going to toggle the data valid strobe and then apply a nibble. So there's going to be a nibble interface. We're going to do a nibble per strobe. 4 bits, a nibble per strobe. And then we're going to use FIFOs, a TX or RX FIFO, to have the software on the processor transmit it to the PIOs. And I did have to have, I guess, ChatGPT help me with this code. It was not the best. There was a lot of issues for the code, and I had to play around with a few different configurations. But we can talk about the 2 state machines we have here. And then we can, work on actually writing better comments while we walk through it real quick. Okay, so for the output one, we're going to do data. It's going to be 0 to 3 at 4 pins, and strobe is going to be 4. And we're going to use the side set as our strobe signal. So we're going to do auto pull. So the FIFO, we're going to automatically pull from the FIFO, and we're going to pull every 32 bits. But we're going to shift after those 4 bits come. So for a word finish, and I think this is like the default, whether shift left or shift right, we're doing some type of shifting on the FIFO when we do every 4 bits. And then we're going to set the data strobe after we set the data pins. So data pins, then strobe, then data pins, then strobe, then data pins, then strobe. Works out really nice. And we're assigning that to a state machine. We're going to do state machine 0, which is PI 0. We're going to the frequency, the side set. This is what we're using the clock. So it's going to be like a clock or strobe. The out base, so we want to use pins. We want to use 4 pins, and then we're going to do the base pin is 0. So we're going to just grab those 4 as the base pins there. And then we just activate the system, and then we can use SM output to push things into the FIFO. And that's going to be the TX. The RX, I had to play around. There's a reason why the strobe is last, because that's how the pins are the happiest. So we're going to read pins 5 to 8 for data. And then pin 9 for strobe. So what we're going to do here, so this is wait for pin 9 to go low. This is wait for pin 9 to go high. Read a nibble. And yeah, we pick the shift direction, threshold. We want to sample this faster because this is a longer state machine potentially than this. This isn't reacting to anything, so it can be a lot faster. So even though this is running faster, it takes more assembly instructions to get through the state machine. If they had little eFPGAs for the PIOs, we could do this really well, but we don't. We got to do assembly. So the assembly, we're going to, I guess, oversample or give that state machine more cycles to be able to accomplish the same thing in the same time frame. And then we activate it, and while there's something in the FIFO, we can get it and then print it out. I think we're good. So we can run the code, and we get this value. We can just add another one real quick, just to be like, to show that we are here and not using some. Okay, Cafe Taco 123 938. This is great, but let's go look at the signals, because we have the FPGA, we have internal logic analyzer looking at the system. We can go ahead and trigger on the rising of the clock. Then we can run this. Okay, and we zoom out, we can actually look at each of the signals. Okay, so here are our 3 sends. You can see, even though that the word is fast, there's a lot of space in between. To reduce that space in between, we have to go get away from the processor and look at more of a DMA transaction. So potentially we could create a read-write buffer in this SRAM on the processor and load that up and be able to do a DMA transaction. But I think this is a great example for doing basic commands between the RP2040 and the FPGA. So we'll look at how to do DMA another time. I just wanted to focus on like getting the PIOs configured correctly, and then we can probably try to set up a DMA later so we can get like large packets of data. So this was kind of step 1. Are there any questions? We have a few people, LinkedIn, Twitch, and YouTube. But do you have any questions about the PIOs? They're a little tricky. ChatGPT is not really good at the PIOs. Claude is not very good at the PIOs. You got to play around with it. Documentation. I'm also using Python. I can understand that also being a little bit of an issue. I feel like if you use the C version of the RP2040, it's a little bit easier, but it's much easier for me to play around with the Python version. I've been enjoying using the Python version of this quite a bit. Let's see if we can get this set up in a way that we can look at this better. Grab this one. That down to like there. Bring this over like this. Go multi-trigger. And then when we run it, data sets up. Let's go ahead and grab all the data. And then we can run this. Oh yeah, it's already running. Run this. Run this. Okay. What we can do is we want to do for in for I in range this. I don't know how big that buffer is. We take out the print statement. Okay, so you probably can tell that print statement messes up a little things. If you want to do data transfers really quick, that print statement needs to go. So let's see what it looks like now. Okay, so we're getting the second transmission over here. So that FIFO, that collection of the FIFO stuff still takes a bit of time. I mean, not a terrible amount of time, but I still think you're gonna want DMA in some form. So we'll have to probably think of some creative ways to do DMA, the setup stuff, and DMA data packet over as one transaction rather than a bunch of these. I guess it's not a big deal. I mean, if the FIFO commands aren't that fast, if you're just gonna write it to data and then DMA over it later, I mean, it's probably still gonna be faster if you just send it as individual writes, because you still have to generate the data somewhere. So the FIFO might be good enough. It's just if you already have preloaded data, like maybe for initialization, if you have some preloaded data in some non-volatile that you want to access and transfer really quickly. But yeah, I don't think there's a good reason to do DMA without like another interface or non-volatile memory. But the command interface will get you some really good latency. My goal is on the board to have the processor handle a DualShock controller. We're going to have the processor handle a DualShock controller, and we're going to have the FPGA handle a frame buffer. And we're going to be able to get the processor to do the DualShock controller stuff, and then the frame buffer in the FPGA. That's the goal. I think it'll be a fun little demo, but this is where we're at right now. Okay, some questions came in while I was talking. Okay, so Peter on YouTube was talking about the DMA in and out. I think it's great. I just need to find something to provide the data. The processor's relatively slow, so we need another, potentially a PIO system to DMA data from another source. So we need to have another DMA-able source that's useful. The PIO input output pin. The programmable IO works for all the pins. So if we go back to this guy right here, the PIOs go to all the 30 GPIO pins. Yes, Julia also asked about strobe as clock. Yeah, I call it the clock in this situation, but it is really a strobe if we want to zoom in on that. So if we look at one of these things a lot closer, it's more of a strobe than a clock. Well, it's an asynchronous clock that's really a strobe. So this is our valid data strobe at the top. We're going from 0, 0, 1, 2, 3, 4, 5, 6, 7. Right, so we're incrementing there. I think I can actually just grab these right here. We can create a new, what I want to do, group. Data. To virtual bus. That's what I want to say. Data. Then we can go take that out of the group. Delete. And then we can name this new virtual bus, call it strobe. So, I mean, this is what we're kind of seeing here, right? 0, 1, 2, 3, 4, 5, 6, 7. Phone is going off, right? No. Okay. Input signal, microprocessor, FPGA output signal. Yeah, we can do that. The role of the FPGA right now, it doesn't have a good role. Right now it's an internal logic analyzer, right? So that's the first step. Right now, the FPGA is acting as a logical analyzer to be able to look at real time at the signals. The goal, we can jump on to the next part. It's a great segue. So let's go ahead and segue into the next part. So the next part is we want to be able to communicate with something in the FPGA. So what we're going to do is we're going to open up my next project, which is using a MicroBlaze RISC-V processor. And we're going to be able to interact with a processor on the FPGA. So it's going to be processor to processor communication. I'm running this too fast. I need to go fix that. We'll fix that later. Figure out what's breaking. So what we're having is we're going to have the Raspberry Pi signal. Okay, go ahead and make it full screen. Can we focus on interface view? Default view. Okay, so we're going to have the Raspberry Pi nibbles come in. They're going to be, let's open up the source for that. Raspberry Pi to AXI. So we have a shift register here, right? So we're going to bring the Raspberry Pi signals in here. We're going to double register them. And when we have a rising edge on that strobe, we're going to push into a shift register. Hard to see. And when the shift register is full, we're going to get the valid signal on this AXI-Stream interface. So now we've converted to AXI-Stream. So we converted that Raspberry Pi 240 communication to AXI-Stream, stick that into a data FIFO, have that data FIFO go directly to the AXI-Stream interface on the RISC-V, and then on the return stream, we have AXI-Stream to the data FIFO, to this 32-bit to nibble divider. And we can open up that here. ChatGPT actually did a great job on this. I gave it the first set of code and asked it to do a inverse of it, and it worked. I liked the code. I like how it worked. There might be some different ways you can do it, but it did a good job. So this is ChatGPT generated. Vibe coding here in HDL actually worked. It was rare. Okay, so this is our next step, right? We want to put something in the loop. One issue about this is we're using a majority of the FPGA right now. I need to figure out that it's mostly the VRAMs. We can probably reduce the VRAMs. I need to figure out a way to maybe simplify the software or use the external SRAM for the frame buffer. But I think we're good there. So we now have a RISC-V processor, so we can have the RP2040 talk to the RISC-V processor. So that's what we're going to do next. But I need to talk about these AXI-Stream interfaces before we dig into that. So let's go do that real quick. So the fast simplex link or AXI-Stream interface is rather not well documented, right? So you have a bunch of these functions. It's a little bit hard to understand how it works. How are we programming the FPGA? So a question from YouTube. So for programming the FPGA, we're using the AMD Spartan 7 FPGA. We're using Vivado, right? And then over JTAG, let's pull up the board real quick. There is an FTDI chip right here. So we're using a USB FTDI chip to program the JTAG on the FPGA. So it's JTAG programming at the moment. So back to the fast simplex link. It's not really well documented. This is really all the instructions you get. Git, put, tgit, or like, this is just what double, right? They don't really describe it well here. That's for like 64-bit. And there's blocking and there's non-blocking. Don't really just go to the software for this. So we're gonna go and open up the IDE, and then I can show you where it's defined in the H file. So we're gonna go here. Okay, am I missing where the other workshop is? This is in use. Have I lost it somewhere? Be running in the background? I just open it anyways. Must be something with the tickles using it. Okay, so we're gonna open, go to definition. So we get actually more information here where we have a blocking read, we have a non-blocking read, we have a blocking control, non-blocking control. I need to go figure out what the interruptible stuff is as well. And then we have is valid, is error. And this stuff is not well documented. I'm going to have to figure out polling version of FSL access macro. Interruptible. I guess it gets it, pulls in, and then creates an interrupt for it. I'm sorry, I gotta go do that sometime. Figure out how that works. But we're just gonna do the get blocking get FSL and the put FSL, and this is just gonna bring a 32-bit value from the AXI-Stream into the processor. And we have a very basic application to demonstrate that. So yeah, let's go ahead and jump to the hardware manager so we can program the FPGA and we can talk through those different things. And maybe we can work on, I guess, timing the latency of it better. So let's go ahead and stop this. Okay, hopefully that works. And yeah, let's go program this. So now if we try to run this code, right? Let's just, we try to run this code, nothing's going to happen because we're no longer connected through the FPGA. So to fix that, we're going to go to the IDE here. And let's go to our code again. This, if I remember correctly. There we go. Now if we, oh, I guess this is blocks. So if we run this, let me get the UART out. There we go, is the UART there for now. So if we run here, it's gonna say hello world, but now it's waiting for this instruction. Now we do this, we get the value, and then the receive side, we must have lost it because we waited too long. Ugh. So we should just try one. Try for a range of 100. And I guess we could do a for loop here as well. For int I equals 0, I is less. We'll just do 25 on the side. I plus plus. And we'll do like E I comma. What happened here? Don't worry about that. Okay, yeah, it doesn't like these commands. That's funny. Okay, and here we want to do, we want to do like FFAA 555500 plus I. Okay, so we built this. We run this hello thing up going. Okay, we're now in this blocking state. Now if we run this, we're not getting all of them, which is fine. Should be getting all of them. And where's our receive side? We should be receiving information back. Okay, let's get back. Go back to where I was before. Save that. Build it. Here, let's. Oh, I'm not printing out. That's why. Print out stuff. Now let's go back to building this. The FIFO should protect us. Now I gotta put like an ILA core to figure out. I guess we do have some bad timing. I might have to look at where the timing is. We run this. And go to terminal out. Now we're going to run this. Oh, the software's already. No, that shouldn't make. Okay, let's try a while loop again. While through. And let's be receiving just fine. Okay, so there we actually got data. I don't know why we didn't get data before. But let's try doing I equals 0. Plus I plus plus 1. And go ahead and run this back to this guy. Oh, you're sending data all across. Let's stop. We go back to here. Let's put that down here. Okay, questions? Yep. So we are running one set of code on the RP2040 and one code for the RISC-V on the FPGA. So the RISC-V is on the FPGA. So the RISC-V is a soft processor for the FPGA in this situation. Okay, rebuild this. Stop this. Now we're going to run. I gotta figure out why we're not hitting everything. Okay. I'll hit play here. And I wonder if we're only sending that. If that was a sending issue. So let me try something again. If we stop this and this would be the output. All of them want me to put a 4 here. So I'm not sure if this is physical or whatnot, but at least it's consistent. I guess we could go to the loopback mode. Let's go program back to loopback mode. I want to see what we get. We'll go debug in the loop mode. Yes, so this is actually a really small processor. Adam Taylor had a really good article about this. So let me pull up that real quick. Adam Taylor actually posted this really quick. It was a really good thing from. Where's his post? So this is a relatively small FPGA. And if we go to his post right here, post this. Post. Okay. That should be good. I'm fine with this. So, it's actually small LUT size, right? This RISC-V processor is using like 2,000 to 5,000 LUTs. FPGAs are easily 50K, 100K, a million LUTs. So on this small FPGA, we're probably using about half of its utilization for the processor, and it's one of the smallest FPGAs out there. So you can easily put a RISC-V soft processor on these FPGAs and get a lot done. Yes, so we're going from here's the FPGA. So this is the design in the FPGA. In the design, we're going to the processor and then out the processor. This way. Go ahead and highlight that. Beautiful red. So this is all in the FPGA. This is all happening in the FPGA. But I want to go try that loopback design again. And see why we're only sending every 4. I didn't really check this before. So going back to our loop design, runs, implementation. Go. Okay, yeah, trigger on this real quick. See if I can see what's happening. Run. And stop. I don't need to go crazy. Okay, let's go ahead and comment out this. Be able to see how quick we can see these signals. Run. Go ahead and stop. And 1 and a 2. So we are sending them. So maybe my counter's off. My counter's off. My my counter is off. There are 8 nibbles, not 32. I know how to fix this. I know how to fix this. This is me throwing away every 4 of them. So I did a counter. I wanted my counter to do 32, but it only needs to do 8. So that's how big the D counter is. And if we do that, that should work. Also, let's look at the implemented design real quick. I just want to see what the timing violation is set into. Maybe we can set up some false paths. And then we can rebuild real quick. Maybe look at the design correctly. Okay. That was some debugging. Thank you for still being on here as we play around with some of these little more nuanced settings. I want to figure out where my massive timing violation is. Where is this? Oh, this is in the process. Okay, sure. We're in the MicroBlaze. What is this related to? Cool. We got the same clock. You just don't want to. You don't want to run that fast. So you just want to requirement, net delay, uncertainty. Okay, show me the details. The details. Yeah, path properties. Yeah, show this guy. Let me see what we got going for us. Negative slack. Why do we have negative slack here? Probably because I'm just running it way too fast. Because the clock. This is the clock. This is our delay. So we probably drop it down to 100 megahertz. That'd probably be fine. Let's go do that. Donor clocking wizard. I'm running this at, so let's just I can run both sides at 100. Yeah, sure, why not? Then it's not asynchronous. So get rid of the asynchronous. Let's get rid of the asynchronous. Do that. Then we're gonna go here and we're gonna say it has common, they're common clocks. Grab that, stick it there. That should be good. Oh yeah, we need to please let me do this inside. Migrate, complete its run. Skip for now. Validate, and then we can build. Okay, so we're going to be running 1 o'clock. We're going to be running the whole thing at 100. And we don't want to see if we make sure we get all the data that way. And let's build it, and we can talk while it's building. So this is the MicroBlaze 5, right? So MicroBlaze, the original MicroBlaze is an older version, right? So let's go look at the, if you go look at the IP catalog in a second, wait till this is happy. But if we look at the IP catalog, there's a MicroBlaze, which is using its own custom ISA, and then there's a MicroBlaze RISC-V, which is using a RISC-V ISA with some extensions for what they've done. Hopefully I can just stand in the background. So that's happy. I won't let me look at anything. Okay. But yeah, so there's 2 RISC-Vs, or 2 MicroBlazes at the moment that they're supporting. Let's see if I can pull up something useful. MicroBlaze versus MicroBlaze V. Okay, I guess this will just do this. So this is their new MicroBlaze 5 processor. It's relatively new, probably like a year and a half old. Even that much. And this is really nice because you can run it on any of the FPGAs. Is there anything else useful? That's for Linux. Maybe we'll get Linux running on it, but not on this board. Do they even talk about the AXI streaming? Really? Such a cool feature. They don't have it anywhere. Like, it's not in this picture here. Where's the stream in and the stream out? They don't have it. They don't talk about it. No, they don't talk about it anywhere. Okay. I like streaming the data in and out. Okay. Okay, here we go. We can go open the IP catalog now. So we look at the MicroBlaze. It's not. Okay. MicroBlaze. So here's the older MicroBlaze. Here's the newer MicroBlaze. And then they had these little systems here that include a bunch of I/O inside of it, kind of trying to reduce LET utilization on the AXI Lite bus. But so there's 2 of them. Okay. Yes. Fine. We can watch the log files. It's going to be so entertaining. But I want to see if we can get this to work and we can see all the data flowing well enough. Okay. Well, we're probably going to have, I don't know, 10 minutes as this finishes. Are there any other questions, things people want to talk about? I'll probably stay on and answer any questions or chat while we wait for this to finish. But I think we have effectively been able to send data from the RP240 to a RISC-V processor and send that RISC-V processor data back to the RP240. Other than that, there is an SRAM interface. Let me pull up the user guide, right, for this board. Okay, so if we look at the Leonardus user guide, we have a nice little block diagram. I guess we just look up here. So we talk about it right here. So there's a 64-bit SRAM connected to the FPGA. I want to use as a frame buffer, which is going to require me to hook up some code. I want to try to. I might be able to use what they call the EMC, or external memory controller. EMC. So we could try using the EMC and connecting up to it. That might be useful. Great question on YouTube. So the question is, so do you develop the program for the MicroBlaze independently from Vivado? So AMD provides two tools, Vivado and Vitis. So Vivado, we define the hardware. So going back here, Vivado, we define this hardware and the addresses, and it generates an XSA file. So if we want to, let me pull it up over here. Let me pull up the XSA file. To do Leon, dig into that real quick. Works out well. Okay, so there's these right here. We're gonna go here. There's these XSA files, which are really zips. So what we're gonna do is we're gonna copy this, and we're gonna rename it as a zip. Okay. Then we're gonna unzip it. So in here, these are basically XMLs and JSONs that describe the system. Oh, what's the easiest one to look at? I think the JSON file will be the easiest one to look at. Oh no, let's do this one. No, they didn't really provide anything useful. The JSON then? Once again, not very useful. No, this file. Okay, so this hardware handoff file, it's a little hard to see, but it provides all the IP, all the connectivity, all the memory information to Vitis. We load the XSA file into Vitis, which makes a platform. And then we can go look at our platform here. So this is MicroBlaze. And if we open it up further, we can look at right here, the drivers, probably where we want to look at first. So we basically have the local memory and the debug UART we're using, the JTAG UART. So if you add more IP to your block diagram, it's going to appear here. It knows how much memory we have. Right here. Where's the memory located? Here's our different packages. Hardware specification. Okay, this is where I like. We can look at the XSA file here. And we have memory, we have IP blocks in use. And we can click here. And, oh, it looks like it gives us registers. So we can actually look at the registers. That's really cool. I actually like that a lot. So Vivado and Vitis are working together to produce the software. So see how we're doing here. We're on op design, and it's still going to be a bit of time. Oh, it just finished. So we're going to do placement next, and then routing. I mean, it's a small FPGA. It shouldn't take too long. But great question on the Vivado Vitis connection. Vitis has a new IDE. It's a tad annoying to set up everything, but it's useful. And like if we wanted to change optimization settings here, I wonder if we did optimize that, if it will operate better on the processor side. But that's good for now. Okay, I see some questions coming in. Okay. Yes, so XSA files are the exports of Vivado. So Vivado, we are making a bit stream for the FPGA and an XSA file to hand over to software. Vitis uses the XSA to generate a board support package for your soft processor. An IP is, I mean, technically it's an intellectual property. In HDL world, FPGA world, we call kind of like standalone modules that are, shipped, published, or whatever IP cores. So we have a bunch of IP cores for different functions, different interfaces, and these IP cores are intellectual property, technically. And so we just call them IP cores. There's not a really good name of module or anything, but it's like I'm going to sell my IP to someone. It's my intellectual property to do this hardware design. And I'm not selling them a product, I'm selling them the design behind it. So we call it an IP core. Oh, look at the bitstream finish. Wow, it did placement and routing way faster than I expected. Hopefully we'll let it finish soon. We can see, make sure we're meeting timing. I slowed down the clock. Okay, bitstream is complete. We'll just let the tool decide when it's done. Okay, we're almost there. Still finishing. But great questions. I do approach this from kind of like higher level approach, like, hey, you should know what an FPGA is, you know what processor is, and all the tools and whatnot. But these questions are great. I'm perfectly okay answering these questions during a stream. We also have a Discord in the description, so if you want to jump into Discord and learn more about FPGAs, I actually think this development board from Adam Taylor's company is really, really good. Having a little Raspberry Pi there with a little FPGA, it's probably not the best bang for your buck when it comes to FPGA development boards, but I do like the functionality that's on it. Okay, we're good there. We met timing. Great. So let's go to Hardware Manager. We're going to program one we just finished. So we need to go to this bit stream. Okay. The dashboard's not going to work anymore. It's okay to delete it. Okay, so let's make sure the software's up and running. So we're going to go ahead and run this guy. So we're going to run, and we should see on hello world. Okay, now we're going to jump over to this guy, and I want to look at this. Now we're just going to run this. Now did I break it completely? Now! Now! I broke it. Let's try the optimization. Maybe the optimization. I just changed the counter. That's all I did was change the counter width and the. Okay. The printout's not working best. Oh, I think we broke it. So, on this. This just broken here? Yeah, I'm not getting anything. JTAG. Might need to stick a small ILA core on it, but there's not enough room. Okay, we might have to play around with that later. Okay, additional questions. The RPi, so the Raspberry Pi 240. So it's not the full Raspberry Pi 5. The Raspberry Pi 240 is a small microcontroller. So we have right here is the Raspberry Pi 240 microcontroller. I'm still confused why this output is not happy about this. So I might, let's kill this and get a new one up and going. See what happens if I run this. Okay, so there's a hello world there. Are you running? Okay, so we're not receiving the data as expected. So somehow we broke this guy. Counter. Oh, that's why I broke it. Supposed to be that. Boot up again. Okay. Well, you want to stick around? I'll still be talking. I should have, built a simulation file and verified the simulation. I should do simulation better. It'd actually be really cool if we simulate this. It shouldn't be hard to simulate. I need to figure out how to load the software in so that it happens for simulation. Okay, next time we do one of these little projects, I'll try to have a simulation file and we can talk about HDL simulation. I'll put that on my to-do list. Prep simulation file. You guys should see it. Test bench and simulations. So like that's how we really do this normally, not just peek and poke at things like this. So we'll talk about simulations. Maybe I can get Coco TV simulation going. I really like Coco TV, and that's easy to do this type of stuff. Try to create something that simulate. Oh, its spawn failed. Spawn failed. We'll let it. I guess we'll let that finish, and we'll try building it again. Okay, there's more questions. Right? Am I just not? The counter counts the clock cycles. Yeah, so for the counter, I have a basic counter here. When the D counter gets to a certain value, it's going to be valid. I reduced it down to 3 bits, but I didn't reduce the end. Because a lot of times people just, put a 000 here and flip back, but I actually put the high value there, so I'll leave it like that. Okay, looks like it's running to the synth design, so maybe we're good. See what happens. What's some other things we can look at? We can look at the ELF file. How many people look at ELF files? So we have a linker script. So this linker script defines where everything goes. This is a GUI version. This is really how you write a linker script. Linker scripts are really annoying. Most times when you have a hardened processor, your linker script is fixed. When you have a soft processor, your linker script can change dramatically depending upon what your soft processor is doing. But in the ELF file, this is your object dump, and we can actually see, we can walk through the software while we wait, because that is something that is terribly fun. So as we set up the CSRs, we're setting zeros to all the registers, we're initializing the stack pointer, and then we're going to jump to start. And then at start, We have our bunch of our global set, our setup platform. Where do we jump to main? Right here. We're jumping to main. So let's jump to main. Main. So here's where the main code is. We're initializing the platform. We're saying hello world, and here's our put FSL. What's a get FSL? Here's our get FSL. Move A5 to T0. Then move. This is our special command, right? That's the printf. That's moving the variable here. And it's at the end. Load. So we're loading a value. Yeah, we're loading -1 and T0. And we call this special command, which uses T0. So then what's the get do? The get. We're just moving. It must be this right here. This is what's loading the word into it. Okay, interesting. Yes, hello world is run on the RISC-V. So this is what's on the RISC-V. And this, no, not that. This is what's on the RP2040. The RP2040 is running MicroPython. That's what's called, right? Is running this MicroPython software, and the hello world is over here. So two processors, two sets of software communicating to each other. So we have a question about simulating encrypted IP cores. So as long as they're using IEEE standards, you should be able to simulate, depending upon their settings, you should be able to simulate with QuestaSim. It's been a while since I've done it, but I believe it's possible. But it depends upon how Vivado and QuestaSim do their encryption. I remember there being a potential issue with that. I think if you look at some of the Vivado release notes, it might have some comments on simulating encrypted. If you encrypt it with Vivado, you should simulate with Vivado. If you encrypt it with Questa, you should simulate it with Questa. The cross encryption simulation support is poor. Also, Jozo was talking about random errors. So yes, Vivado and Vitus do have errors that pop up, but in general, when I compare it to other, we'll say FPGA development tools, I do feel that they are somewhat better than average. A lot of these tools are supporting a lot of possible configurations of hardware, software on top of the hardware. FPGAs are very complex. It's really hard to hit all the corner cases. But yes, the software can be a little bit buggy, and it's a little bit nerve-wracking sometimes to demo it live on stream. Okay, we're almost there. Good. We are ready to go. Hopefully it works this time, and I don't need to commit to trying to do simulation or on debug. Oh, okay, we're flying. We're good. There was a lot of data. Let us stop here. Let's reprogram the FPGA and try again. We might have got off center because they have it on center. I need to put a debug feature into the streaming interface. Here are the hello world stage, and now let's run this. We are getting off centered. A5, A5, 1, 2. We missed the first byte. Why did we miss the first byte? We missed the first nibble. We could try the best way to do this. I understand missing the first nibble. Otherwise, it's going good. It's not screwing up. So we missed the first nibble. Also, what's happening here? Are we just not fast enough? We're missing, we should do AA55 and then 2 zeros. AA550. Like we're missing nibbles. Maybe we do need to run this one faster. I might need to do this one at a faster rate because we're missing nibbles. This should be AA5. But we're clearly missing the nibbles. So we're not sampling this at fast enough. That's interesting. Wasn't expecting that. Yeah, so we are losing data. We need to increase the sample rate, or we need to decrease the send rate. Oh, we do it at 120. I guess we could do it at yeah, let's just do it at 100. Stop here, reprogram the FPGA. Go here, we'll run this. Wait till we get to a good state. Where's my hello? Do I need to set this up again? Okay, looks like we lost the terminal correctly. So let's go here, type another JTAG terminal. Try running this again. Let's see if we can get the... Okay, very good. Okay, that's the hello world we want. Now if we go over here with a slower clock speed, what do we get? Okay. Ooh. We are still missing data. 3, 4. Okay, let's try really slow and see if it's the issue. Otherwise, it's a logic issue. It's also my fault. We can figure that out later. Okay. You clearly want me to do this again. You don't like it when I reset these things over. Okay. Oh, it's still running. It didn't stop. I have to stop it. Back here. Stop. Still do this for or we're gonna do 100 and okay. Stop. Close. Try this the best way possible. Program it, set the JTAG UART, and run it. JTAG UART. Here you are. Let's go back here. Okay, run. Hello world, we're ready. Go back over here and run. Look at that. Beautiful. It stopped. I think I know why it stopped. Why is it not transmitting? Transmitting just fine beforehand. just send it again. That's confusing. I guess we could put a blocker. Do like a blocker here where it waits for the first one. I'm curious, does it wait? It's waiting. Try running this again. Ah. Okay. That's probably where we're gonna have to end the stream today. We've done an hour. I will play around with this off stream to try to get up and running, and then we can post a code somewhere. But we can talk about it more later. I just need to play around with timing. It's probably some timing thing of the system. I'm really confused why this just stops. The FIFO on the other side might be getting full, but we were receiving data just fine beforehand. So we went back to that while loop. All true. Does sound like I probably need to get off soon. But yeah, so I'm gonna try running this one more time. Stop that. Kill this. Program the FPGA. And look at Vitus. JTAG UART working. Here. Run this. Okay, that's ready. Now we go over to this while loop. And we're just going to run. Okay, we're getting the code back. That's good. That's good. That's good. You're still going. You're still going. You're still going. Okay, that worked. It seems to have an issue getting stuck there. Okay. Well, thank you for joining me. Well, I'll debug it more and I'll post it online, or we can talk about it next video. But kids are home. So time to get back to my other chores for the day. Feel free to join in next week. FPGA Zealot. We have a stream on Tuesday, probably next Saturday. But thanks. Leave a like.